Okay, today's lesson is about solving rational equations. Now, we've talked about what solutions are. In general, specifically, as we've dealt with them with quadratics, we know that solutions are where the graph crosses the x-axis. This point's otherwise called the x-intercepts. Now, we've also solved systems of equations where we find the intersection of two lines. That's going to be helpful also. And with our linear equations, we often just solve for the variable, like we get x by itself. So all of those concepts are good to refresh ourselves on as we go into solving rational equations, because each equation we may have to use different methods. So we want to be keeping all of those ideas about solutions in mind. Now we have several methods for solving rational equations. We can isolate the variable, and again, this is like we typically do with a linear equation, solve for x. We factor. That can be factoring into two binomials or factoring a GCF out. We typically do that with our quadratic equations. We can cross multiply. This is something that we have done with fractions, remembering that cross multiplying can only be done across an equal sign. For instance, something that looks like 3 over x equals, that is a 3, I promise, 3 over x equals 1/2. So we cross multiply and we get x equals, once you multiply that one time, you put your equal sign down, then you multiply the other two and set it equal. So just a few rules, some of the mistakes that I see as students do cross multiplication, just want to refresh everybody on that. So let's erase that and go on with our methods. Eliminate the denominator. This is something we probably haven't done, but as we work some of these examples, we might need to do that, or just give you an option to do that instead of getting least common denominators. And then finally, we've got our calculator. Now, there's two different things we've done on our calculators to help us solve equations. We can find the zeros. That's what we typically do with our quadratics and our cubics that we have done. But if you remember when we had systems of equations, we could put one side of the equation into y1, one side into y2, and then find the intersection of the two lines. So that could possibly be an option here also. So go ahead, write these down and have them in front of you so that as we go through solving our problems, you've got this list to pick from. Now, the most challenging thing about solving rational equations is usually you're not going to use only one of these methods. You're going to have to use some of them together to get all the way through the problem. It's not something that feels normal right now, but with practice, you'll understand it and be able to figure out, oh, I need to use this particular method in this situation. So just stick with the frustration as you're working through it, and we'll get you there. Alright, so let's start some examples. Okay, actually I almost forgot, before we go on to the examples, we have one more definition. An extraneous solution. I know this is a funky little word. An extraneous solution is a solution you get from correctly working the equation. You've done everything mathematically correct, but it doesn't actually work. Usually that is because it's a restriction to the original problem, which is why it's so important for us to find the restrictions on the original problem. And then when we get done solving, we can compare with the restrictions to find out if it's a good solution or if it's an extraneous solution. Alright, now let's do our examples. Okay, our first problem is 12 over x plus 5 equals -2. Now, if you are in my actual class, this is number 1 on the worksheet that we were working off of today. Now, I've always told you guys, if you are given a rational equation and it has a whole number, always instantly put a 1 under that whole number so that you can see it as a fraction. Now, we are going to do our restrictions first. I'm just going to come over here and put a capital R. And I've got x plus 5 equals 0. subtract 5 from both sides, so x equals negative 5, or x cannot equal negative 5. Since my 1 right here doesn't have a variable with it, we do not need to worry about a restriction there. Alright, so I have a single fraction equal to a single fraction, which means I can cross multiply. So I'm going to put parentheses around my binomial so that when I cross multiply here, I remind myself that I am distributing that negative 2 to both the x and the 5. So I've got negative 2x minus 10 equals. Now I am going to cross multiply the 12 and the 1. Notice I put the equal down first. That's a common mistake I see with cross multiplication, is you guys drop that equal sign. Well, at this point I have a nice beautiful little linear equation, so I'm just going to solve for x. So I am going to add 10 to both sides, and I get negative 2x equals 22. Now I'm going to divide both sides by negative 2, if I can get my pen to write. And that gives me x equals negative 11. Now we can check this by plugging it back into the original equation, or if you've got your calculator, you can graph it and see if it crosses the x-axis at negative 11. Now, we need to compare. It is not one of the restrictions we found, so this is my solution. And we are done with the problem. Let's do the next example. Alright, so here is our next example from the worksheet in class today. This is number 3 off of the worksheet, which is why I'm labeled it number 3. We need to find our restrictions first. So here I can see if I set that equal to 0 and add 5 to both sides, I get an x can't equal positive 5. Now this trinomial here, I need to factor before I can set anything equal to 0. So we get x and x, plus and minus, factors of 35, I'm going to pick 7 and 5. Okay, if you're not seeing how I did that, go ahead, pause and do your process or put it in the calculator. Now here, I've got an x minus 5 just like I did over here. I don't need to repeat that. It's already been done. But for this x plus 7, I'm going to have the restriction x cannot equal negative 7, because if I set that equal to 0 and solve for x, I'm going to subtract the 7 from both sides. Alright, so we've got our restrictions. Let's go ahead and solve. So to do that, I'm going to go back to the original trinomial. You can cross multiply with that factored form, but I know what's going to happen, so we're going back to the trinomial. It's usually better to stick with the trinomial or even a binomial in the beginning, because most of the time we end up being able to combine like terms. So let's go ahead and do this. I am going to cross multiply, so I get, putting my parentheses around that, I get 5x minus 25 equals, you notice I'm always putting my equals down before I draw that other line to multiply. 1 times the trinomial gives me just x squared plus 2x minus 35. Nothing changes there. Okay, this is something that we want to watch for. When you've got an x squared term or terms, and you also have x terms, if we cannot move these terms from one side of the equal to the other and cancel them out, then we need to work with them. And what I mean by that is we want to go ahead and move everything to one side and set our quadratic equal to 0. If you remember, we used to do this when we were working with quadratics as a unit. So we're going to subtract 5x from both sides. Now notice I am putting it under the 2x. And I'm going to save some room here as we're working. I'm going to go ahead and add the 25 to both sides. Okay. So what that leaves me is 0 on this side. I'm going to bring down my x squared because I did not add or subtract anything to that. I have a positive 2x minus 5x, which is leaving me negative 3x, and then a negative 35 plus 25, which leaves me a negative 10. So right now I have a quadratic trinomial equal to 0. Well, we did this all the time. If I want to solve a quadratic, I'm just going to factor. So I'm going to go ahead and bring my 0 down. I'm going to factor this quadratic, x and x. This last sign is negative, so I'm going to have a plus and a minus. And factors of 10, I'm going to use 5 and 2, because negative 5 plus 2 would give me the negative 3 in the middle. Again, if you're not seeing how I do that, go ahead and pause, do whatever process you like, or use your calculator. Now, at this point, I have two factors. This times this equals 0, so one of those has to equal 0. So x plus 2 equals 0. Subtract 2 from both sides. I get x equals negative 2. Same thing over here. X minus 5 equals 0. Add 5 to both sides. X equals 5. So I've got x equals negative 2 and x equals 5. I've got two possible solutions. So let's go back and look at our restrictions. Okay, I notice here I have a restriction of x cannot equal 5. And down here I have x equals 5. So this is where we get an extraneous solution. So x equals 5 is extraneous. That says it's not actually a solution because it is also a restriction. It can't be used. But x equals negative 2 is a good solution. All right, let's do another one. Okay, here we have 5 over x equals 25 plus 5 over x. Now, on both of our previous examples, we have cross-multiplied. We cannot cross-multiply here because I do not have one fraction set equal to one fraction. I've got this 25 plus in between here. This plus tells me I cannot cross-multiply. Alright, so this is one of those situations where, okay, we've got to think about this. We might need to use another method. Well, right off the bat, I notice that I do have two things that are the same. So I am going to go ahead and subtract 5 over x from both sides. I'm going to try to get both of these x terms on the same side. Well, when we do that, 5x minus 5x cancels each other out. Bring down my 25, and this 5x minus 5x cancels each other out. Well, I don't have a variable left. So 0 equals 25. This is not a true statement. That does not make sense. So this is what no solution looks like. When you lose your variable and there's nothing that makes sense at the end. Okay? Now, we forgot to do our restrictions. I even put my little r over there. In our original equation, I had just x in my denominator. So x can't equal 0, which at this point, it doesn't really matter because there's no solution anyway. Okay? Let's do another one. Okay, this is our last example. I've got a single fraction set equal to another single fraction. So I can cross-multiply here, but we are going to remember this time to do our restrictions. So for the x squared, Square root of 0 is 0, so x can't equal 0. Now the x squared plus 2x, I'm going to come over here. I'm going to go ahead and factor a GCF out. I'm going to factor an x out of there. So I get x plus 2 equals 0. So here I can see x can't equal 0 here either. And here, x plus 2 equals 0. If we subtract 2 from both sides, x cannot equal negative 2. So I've got two possible restrictions on this one. Okay, so let's go back to the original problem. Let's cross multiply. I'm going to do 3 times x squared is 3x squared equals, I'm going to put my parentheses around my binomial, and 6 times that gives me 6x squared plus 12x. Okay, now remember, I told you that if you have x squared terms and x terms, think about, can I cancel them by moving them from one side to another? Well, if I move this 6x over here, that's not going to make 0. So we're not going to do that. So I am going to move this 3x squared over here, and we're going to set our quadratic equal to 0. Okay, so minus 3x squared minus 3x squared leaves me with a 0 on this side because they cancel. 6 minus 3 is 3x squared plus 12x. Okay, so I have a binomial set equal to 0, but it is a quadratic. So what do I do with my quadratics if they're binomials? We look for a GCF. This has a GCF of 3x. So 3x squared divided by 3x is x, and 12x divided by 3x is 4. So now I'm going to take each individual factor. 3x equals 0. Divide both sides by 3. X equals 0. And then x plus 4 equals 0. Subtract 4 from both sides. X equals negative 4. So I've got an x equals 0 and an x equals negative 4 as a solution. But remember, we've got to look up here. I've got an x can't equal 0. So this one is extraneous. It's a funny little word. But x equals negative 4 is a good solution. That will work. So I've given you 4 different examples, very different examples, lots of factoring, and your assignment tonight, if you're in my class, is to do the evens 2 through 10. Email if you have questions.